Hello, welcome. Today I'll be telling you about Tabby, our approach to tabular and structured data synthesis with large language models. In recent years, machine learning research has made a lot of progress on the text and image modalities, leading to well-received LLMs such as Gemini, GPT, Claude, and Llama, as well as highly performant image foundation models including Sora, Nano Banana, and Midjourney. Meanwhile, tabular and structured data modalities have been more overlooked and as a result don't have general foundation models available, despite tabular and structured data being highly ubiquitous across many fields. We are aiming to borrow some of the advancements in the text modality into the tabular and structured modalities with our technique called Tabby. The insight here is that we are able to convert any transformer-based large language model into a tabular model using a mixture of experts modification with routing based on the column index. On the left half of the screen, you can see a comparison of a base LLM, is what we call the LLM that we are beginning with that doesn't have Tabby, against the Tabby modified large language model. So on the far left, you can see the final transformer block is followed by the language modeling head in a normal large language model. While in the Tabby model, we swap out that language modeling head with a set of heads where we have one language modeling head for each of the columns in our tabular data set. As a result, each of these heads is able to specialize and to model its specific corresponding column, while earlier parts of the model are shared across all of the columns to learn the relationships across columns in our data set. For our tabular evaluations, we find that Tabby performs quite similarly to non-synthetic data. We compare against 13 different baselines on 8 data sets and find that Tabby is the #1 best method in 5 out of the 8 data sets. And as you can see in this performance profile image at the bottom, which is a way of aggregating our performance across the 8 different data sets and visualizing this, the dotted line is the performance of non-synthetic data, which is our upper bound. And Tabby, which is the purple line, performs quite similarly to this non-synthetic data. We find that according to our primary evaluation metric, which is MLE or machine learning efficacy, Tabby achieves parity with non-synthetic data on 5 out of 8 data sets. You can refer to our paper for our entire main results table. And I also encourage you to check out the appendix where we have several more metrics that also support this story, as well as the very useful membership inference attack metric for assessing the privacy, where we show that Tabby, while achieving state-of-the-art tabular synthesis performance, does not pose any additional privacy concerns compared to prior SOTA synthesis techniques. Our next set of evaluations focused on structured data, and in particular, we look at our ability to generate glaucoma patient records, which are in a nested JSON data type. We find that Tabby is the only approach that is capable of learning the unflattened JSON structure shown in the image in the middle of the slide, and is also the only approach that achieves parity with the non-synthetic data on this JSON data set. The trick that we use here is recursive experts, which you can see in the bottom right corner of the screen. Instead of replacing the language modeling head with a set of V experts, one for each column, as we did for tabular data, we actually replaced the language modeling head with a tree, as you can see in the purple boxes in the image, where that tree mirrors the shape of the data set. So those nested boxes that are in the middle level of the tree, those correspond to the red items. So in particular, disk and rim info in the image. And then we have the heads that are in the bottom layer of the tree, the leaves. And those model the blue items, the teal items. So size, ratio, pallor, color, and bayoneting. So as a result, our model is shaped the same way as our data set and is able to learn this unflattened JSON structure and generate JSONs natively rather than trying to impose that structure on a large language model that will struggle to learn it a little bit more and as a result Tabby outperforms these methods that have to learn the flattened JSON. Another unique capability of the Tabby model is its ability to learn what I call non-categorical strings. And so these are features with things like names, ID codes, phone numbers, and addresses where you want your model to learn the structure, the syntax of your features instead of memorizing the exact values that occur in your training data set. So that then at sample time, it's able to produce novel features, novel names, novel phone numbers and addresses rather than those exact ones that occur in your training data set. This would be useful in an application such as medicine where you want novel patient data to be produced rather than just producing the exact same patient data that occurs in your training data set, which would lead to some privacy concerns. This technique, this ability of non-categorical string modeling is not supported at all by prior approaches. Any of them that are diffusion-based, GAN-based, or even the prior tabular large language model approaches don't support this. Meanwhile, we find that after less than 5 minutes of training, Tabby is capable of successfully learning the internal structure of our synthetic data set that is displayed here. And its resulting samples, 99.9% of the rows display valid syntax, matching the rules of our original data set, and only 0.1% of the rows that were produced had a value that was contained in the training data set indicating memorization. So that is a very low rate, indicating that Tabby was, after this very short period of time, able to learn the actual structure of these data features rather than simply memorizing them. So to recap, Tabby is a mixture of experts-based technique for converting any transformer-based LLM into a tabular model, and it achieves SOTA tabular synthesis performance while also being able to handle non-tabular structured data and non-categorical strings. We're very excited to share this method with you. As you can see, there's these QR codes on the right side that will lead you to our paper as well as our GitHub code base. And I would be happy if you would reach out with any questions that you might have, comments or otherwise. My name is Sonia Kromp, and you can see my email and website at the bottom of the screen. Thank you very much and have a good day.